Good morning. Today we're going to talk about Fiber Bragg Gratings, abbreviated FPG. Let me move this toolbar around. Sorry, it's going to be, sorry for the silence. All right, we're going to talk about Fiber Bragg Gratings, and the principal emphasis is going to be filtering out a given wavelength of light by reflecting it. All right, here we see a picture of a Fiber Bragg grating. And you notice at first it just looks like a regular piece of fiber. Then we notice in the middle here, you got a ribbing. What is actually happening is we have alternating layers of different indexes of refraction. We have usually the index of refraction of the core, the regular fiber. Then we have a higher index of refraction for a given layer. Then we're back to the fiber. Then we're back to the higher, fiber higher, and so on and so forth. The other thing that this slide does a nice job at demonstrating is what happens. The fiber Bragg grating is going to reflect a certain color of light, a certain wavelength of light. Here it's reflecting the blue, but allow other light, such as the yellow, to go straight through unimpeded. This is a cross-section of a fiber Bragg grating. What you should notice is the nice even periodic spacing of the indexes of refraction, where we have the core's index of refraction and then a higher index of refraction. This figure here basically demonstrates the index of refraction as a function of length. So here we start seeing the layers of higher index of refraction. All right, the use of Bragg filters. We've previously talked about Bragg filters being used to correct for chromatic dispersion. So they still do that. They're used for laser stabilization. They can detect strain or temperature in a fiber cable. And what we're going to be concerned most about is creating a notch filter for a given wavelength of light in an optical add-drop multiplexer. All right, what's a notch filter? Well, this next picture shows a good job of showing what a notch filter is. What I would like you to notice is we have a nice even distribution of light here. All the colors are represented equally. And that goes into the fiber Bragg grating, which I'm just going to call grating, goes into the grating. The transmitted part, we notice that there is a notch, a given wavelength is missing. The green yellowish color is missing. And we also notice that some of the light is reflected, a little bit of the other colors, but the majority of the green yellow is reflected. That's why we don't see it here. If we were to add this diagram here on the left with this diagram here on the right, we'd get back to the top diagram where everything was represented equally. So we're subtracting out the yellow-green color. And again, this is in the parlance called a notch filter. We have a notch filter on the green-yellow wavelength. All right, the way this works is something called constructive interference. At each layer, each interface, some of the light is reflected and some of the light is transmitted. And what we do is we carefully choose the geometry of these layers so that the reflected light adds up. We would say that the electric field add. A little bit less precisely, we can say the intensity of light adds. So all five of these beams add their intensity, And if we have enough of these interfaces between the high and the low, enough layers, we can actually reflect 99% of the original incident wave back out in the direction that it came. Another important point is given enough of these interfaces, no light of that given color gets through the fiber Bragg grating. So it basically drops that color from the distribution of colors. All right, if we talk just a little bit about the geometry, each of these layers, you take the width of this layer multiplied by the index of refraction, and that is going to equal 1/4 the wavelength that we want to block. Notice that the darker blue with the higher index of refraction is shorter because n times d. The regular core index in the lighter blue is longer because its n is smaller. Then if I want to tune the notch filter more precisely, so the spread of the notch filter as a function of is a function of indexes of refractions. The spread decreases with the difference of index of refractions. Said in English, if I want to make a very narrow filter, what I'll do is make the darker blue be a very high index of refraction, 2.5, 2.8, maybe as high as 3, whereas I would leave the regular core index at 1.5. So the bigger the difference between the two, the more precise the notch filter is. All right, we can have different types of Bragg gratings. Up to now, we've been talking about the type called uniform because the layers are a uniform width and they're spaced at uniform spacings. But we're going to learn that there are at least 4 different types of fiber Bragg filters in use. This one's a little bit of a tricky one to say. Adposizing sections. We don't have a picture of that. We'll talk about that in a moment. And aperiodic index modulation. Basically, notice how these layers of higher index of refraction material, the gray layers, get bigger as we go along the length of the fiber. We can have a tilted fiber Bragg grating. So this is at a little bit of an angle with respect to the core. And then there is a superstructure fiber Bragg grating. What it basically says is I have a little grating. See the 3 variations here. But out of that pattern of 3 variations, I make another pattern. And that is called a superstructure, a pattern of patterns, a structure of structures. All right. Now, an adposing section. Adposization just means to smooth a jagged curve. Um, Adposization is used to improve focus by removing airy disk by diffraction. Okay. So what we should do is we should take a look at these pictures and notice we have the central focus, the light that would be used, but there's a lot of light, a lot of energy wasted in these discs here around the center. Here it's nice monochromatic laser light, but here notice that there's different colors and the center seems slightly blue. And then the area rings are different colors. Well, this means that I'm going to have more chromatic dispersion with my area diffraction. So what we're going to do is just add podation means to smooth the jagged curve. We're not going to have that stark interface where we have high, low, high, low, high, low, high. We're going to vary the index smoothly. We'll ramp it up, or ramp it down smoothly. Basically, the ad.by's Fiber Bragg Grading gives us a nice trade-off. It says we're going to trade off between side lobe suppression, that's these extra airy disc, and maximum reflection. Now, our main concern is an add drop multiplexer. In an add drop multiplexer, we don't use the reflected beam. We're just throwing that part away. So it's a good trade-off to trade off some of the reflection to suppress these side lobes. Adpodizing sections. Say that 50 times fast. All right, an aperiodic fiber Bragg grating. It's also known as a chirped grating. Okay, the layers of index, the higher layers index thickness is varied to increase or decrease along the length of the fiber. So if we go back to this picture, we notice that, go back to this picture, go back to this picture, we notice that the chirped fiber Bragg grating is has these layers of higher index of refraction get wider and wider and wider. So it could uniformly go to wider, wider, or we could actually make one where it goes narrow, narrow, narrower. So the reason we use these aperiodic fiber Bragg gratings is for dispersion compensation. We can broaden the reflected spectrum. So here on my adposizing sections, we worried about narrowing. Skip the last 60 seconds. Before we worried about narrowing the wave band of wavelengths blocked. If we want to widen that bandwidth, what we're going to do is use an aperiodic fiber Bragg grating. We can use it to monitor temperature along the length of the device. And when we talk about lasers, we're going to talk about pulses of light traveling down the fiber. And it is better if the pulses are nice and compact. Well, the aperiodic fiber Bragg grating can compress a laser pulse. All right, a tilted fiber Bragg grating. It can also be, it doesn't have to be, but it can also be chirped. The tilt is only a few degrees. It reduces Raman scattering. All right, Raman scattering, it's prevalent when we have high power going through our fiber, like we're using high power lasers. Raman scattering, to be fancy, causes undesirable nonlinear effects. What's that mean? Well, we're hoping that if we send two different wavelengths of light down the fiber, that they don't interfere with each other. They're independent of each other. It doesn't matter the other one's there. Well, with Raman scattering, the two will interact, distorting both waves. So we don't want those effects, so we can use a tilted fiber Bragg grating. The superstructure is also known as a long period grating, and I like to describe it as a pattern. See the pattern of I'm repeating 5 of another pattern where I'm repeating 3. So the superstructure FPG has the following applications. Anywhere where the precise wavelength filtering has to be done with multispectral features. This is going to be done for our dense wave division multiplexing, for high resolution sensing, and for optical signal processing. Okay, so What we have done is we have talked about Fiber Bragg Gratings and how they can be used to affect a notch filter, reflecting the undesired wavelength of light. We learned that Bragg gratings use constructive interference, and we further learned that the index of refraction in a fiber Bragg grating can be varied to optimize the fiber's optical properties. Okay, that's it. Stop share, stop video.